three simple broadcasting rules. Rule 1 tries to match the rank of input arrays, and if the rank mismatches, it prepends the array with the smallest rank with 1 and keeps on doing until both arrays have same number of axes. For instance, if we want to add this two-dimensional or rank 2 array into this rank 1 array, first the rule 1 will be applied, and rule 1 will try to prepend 1 in this array and will transform its shape from 3, 1 to shape 1, 3. At the end of rule 1, both the arrays will have same number of axes. Then comes the rule 2. Rule 2 tries to match or check whether both the input arrays have compatible shapes. Two arrays are said to be compatible if either their corresponding axes or have same values or one of them is equal to 1. Finally, rule 3 of broadcasting is applied. Rule 3 of broadcasting simply ties the array along all the axes with shape value equal to 1. For instance, if we want to add this 3, 1 array into this array of shape 3, first the rule 1 will be applied, which will transform this array shape from 3, to 1, 3. Then the rule 2 will be applied. Since both arrays have same shapes, we will move to the rule 3, and rule 3 will tile the arrays. So this array will be tiled along the axis with value 1, which is basically horizontal axis, so it will be tiled in horizontal direction, and this array will be tiled in vertical directions. So at the end of rule 3, we will have two arrays with identical shapes, and finally an element-wise operation will be performed among both the arrays. It is important to mention that at the end of broadcasting operation, if still both the arrays have different shapes, a shape mismatch error will be generated. This completes our discussion on broadcasting. For further information, you are requested to check out the official documentation. Let's now compare the performance of vectorized and non-vectorized code to see how much gain in the speed we can achieve using Numpy vectorized code. Let's write a pair of simple functions to compute sign of the values in the range using both pure and Numpy. Let's start by writing Python function. So we are going to write a function which will receive 3 arguments: start of the range, end of the range, and step size. And first we are going to create the output list, which will be used to store the computed values, and its size will be computed as the difference between the range. In fact, it will be a range SS range divided by step size. Now what I will do is that I will iterate over this sequence and compute the sign of each value in the sequence. For I in range of length of result, so the result of I is equal to sign of S range, and at each iteration I will simply increment S range by step size, and that's it. I will simply return result. So once I have written this Python code, now I'm going to write a corresponding vectorized Numpy code. Def sign vec. Once again, it will receive 3 arguments: start range, end range, step size. And now I will compute all the elements in the sequence using a range. So values will be np dot a range of start range and range and step size. And now I will simply return np dot sign of value. That's it. Now once we have written the code for both the functions, we are going to use the IPython magic command timeit. Timeit runs the given code for asked number of times and return the average running time of best runs. So now let's timeit the sign function written in pure Python for 10,000 times. And now let's go and timeit the Numpy code. You can see that Numpy code is order of magnitude faster than Python code. Precisely, it takes 11.5 microseconds per loop compared to 216 microseconds per loop taken by the pure Python code. Here are some tips for writing vectorized code. Writing vectorized code requires shift in thinking. That is, now when thinking about the operation, one has to think at the level of operations over complete arrays or their axes instead of single variable. Secondly, one has to always keep in mind the axis and shape while performing basic operation. Keeping axis and shape in mind can really help to visualize the computations and debug our code. np.revel, np.reshape, np.concat, np.newAxis and np.skis can be extremely helpful during the vectorization of code. However, one has to remember that vectorizing using broadcasting or stacking can make our operations memory intensive. So one might have to trade off between space and speed at many occasions. This brings us to the end of the tutorial. Finally, I would like to say that I find this book, Python for Data Analysis, indispensable for data scientists. Thank you.